Hello there, this is Coach Ikram, and welcome to this video on thermochemistry. In this thermochem unit, we're going to be looking at how heat is flowing between a system and its surroundings. My system is always going to be the reaction or the process that I'm actually investigating, and the surroundings are going to be everything else around that, the glassware, the table, the air, etc. When we're talking about this heat flow, it's important to remember the law of conservation of energy. Energy is neither created nor destroyed, but it can be transferred from one form to another. And in this unit, we're going to focus on the transfer of that energy between different objects and the kinetic and potential states associated with them. So for example, when we're talking about heat flow, we're always going to be talking about it from the point of view of that system or the substances that actually start the process. So if I'm looking at ice, when it melts, it's taking in energy. So we've got ice here, and it adds heat to it, takes in that energy, and it's going to melt to get to water. This is going to be an endothermic process because the ice, which is my system, is going to be gaining the energy. If water freezes, energy has to be released. So we've got liquid water, and in order for it to become solid water, it has to release that heat. And because ice, that system, is losing heat to the surroundings, then it's going to be an exothermic process. When we're focusing on our heat changes in thermochem, we're going to be kind of looking at it graphically. And over here on the left, we've got an energy diagram, which we're actually going to see quite a bit. And this energy diagram shows the relationship between the potential energy of my reactants, or what I start with in my thermochemical reaction, and my products, what I'm going to finish with. On the right-hand side, we've got a diagram that shows you the relationships between gases, liquids, and solids, and what processes we use to get between all of those. So for example, between a solid and liquid, if you melt and you go from a solid to a liquid, that is fusion or melting. And if you go from a liquid to a solid, that is freezing. And all of these terms between gases, solids, and liquids should actually be fairly familiar to you. The capacity for doing work or actually producing heat is what we call energy. Kinetic energy is going to be your energy of motion. When energy is stored in the bonds of a substance, however, it's going to be called potential energy. So for example, when you've got a car and it's burning gasoline, the energy that's stored in the chemical bonds of that molecule is then going to be released to do the work. So now we're going to talk about heat. And when we talk about heat, we use the variable Q to define it. And heat is energy that transfers from one object to another because of a temperature difference between them. The international or standard unit, the SI unit for it, is going to be joules, or capital J. Heat is always going to flow from a warm object to a cold object. Heat as energy can also be measured in calories. And when we talk about food, those calories are what we call kilocalories. The important thing to note about heat, it is not temperature. Heat is not temperature. Temperature is simply a measurement of the kinetic energy. Heat is an energy that is transferring from one object to another. Enthalpy, or capital H, is going to be the internal energy content of a system plus the product of volume and pressure that system is at a given temperature. We cannot measure enthalpy directly, but we can measure the energy that's lost or gained by a system when the reaction takes place. And we call those values the change in enthalpy, or delta H. This is also known as the heat of reaction. So when we're looking at it, that means that my delta H, or my change in enthalpy, is going to be equal to my Q value. And it's also going to be equal to my products, the enthalpy of my products, or the energy of my products, minus the overall energy of my reactants. There are four types of energy that we're going to discuss in thermochem. The first is kinetic energy, and this is going to be due to the motion of a substance's molecules. Light, heat, sound, mechanical motion. Temperature is going to be a measurement of the average kinetic energy of that substance. The second type of energy is potential energy. That is stored energy due to the position or arrangement of it. For example, a rubber band right before you pop it off. Thermal energy is going to be the total of kinetic and potential energy of a substance caused by the composition of that substance and the motion of its atoms, ions, and molecules. And chemical energy will be the energy, the potential energy that is stored in the bonds between the atoms in a substance. Every single reaction involves some sort of change in chemical potential energy. Reactants transform into products which either have more or less potential energy than the reactants that you started with. And that's going to lead into having exothermic or endothermic reactions. So for example, if I have an exothermic reaction, my system is going to lose heat to surroundings. The heat flow out of the system, and the heat is going to be expressed on the product side of a reaction when we write out the full chemical reaction for this. It's going to have a negative change in enthalpy, and therefore a negative Q, or my heat. Endothermic, and the system is going to gain heat from the surroundings. So the heat flows into the system. The heat's going to be expressed on the reactant side of the reaction, so on the left, and it's going to have a positive enthalpy and therefore a positive heat value. When we're looking at it from a graphic standpoint, on the left-hand side, we've got an exothermic reaction here. So if you'll notice, if this is a measurement of the energy in my reactants and my products, I've got potential energy of my reactants is up here. I'm overcoming an activation energy, which is the energy required in order for that reaction to take place. And then I'm going to lose energy down to my products right here. So you notice that my products are actually at a lower potential energy than my reactants. That means this is going to be exothermic. The difference between the products and the reactants is my energy that was released, making this exothermic. So the potential energy of my system goes down. The thermal energy of my surroundings will go up, and this is going to feel hot if you were to touch this system. And this is an exothermic system. Right, I've got an endothermic system. So if you notice, I've got my reactants down here with their potential energy. Overcome that activation energy in order for this reaction to take place, and my products end up here with a higher potential energy. So that difference between the products and the reactants is going to be a positive H, and that's my energy absorbed, making this a endothermic reaction. So summing that up, the potential energy of my system in this case goes up, but the thermal energy of my surroundings goes down because that energy was transferred into my reaction and into my products. And so this is going to feel cold. Some examples of this: evaporation of alcohol is endothermic. Water cooling and leaves burning are both exothermic. Ice melting and boiling water is endothermic, and freezing water is exothermic. So if I'm talking about my energy curves, if I've got A plus B yields C, so these are my reactants right here, yields C. If I have A plus B down here, overcome my activation energy, and C is higher, that means my difference in my potential energy, my products have more potential energy than my reactants, and therefore my reaction is endothermic because heat is gained. Okay, so let's practice actually reading a reaction diagram. So if you look over here on the left, we've got our reactants and we've got our products, and that's important to note where those two are on this energy diagram. So the energy of the reactants, the total potential energy of all the reactants in here, if we read it, is at 150 kilocalories per mole. The energy of my products down there on the right is at about 50 kilocalories per mole. My enthalpy, my change in enthalpy, is going to be the products minus my reactants. So in this case, 50 minus 150 is going to give me negative 100 kilocalories per mole. So overall, this reaction is going to be exothermic because I have lost energy going from the reactants to the products. Looking at another one, my reactants in this case are at 100 kilojoules. My products are higher at 300 kilojoules. If I was finding the change in enthalpy of this reaction, my products minus my reactants, that's going to be a positive 200 kilojoules overall. Which letter on the graph represents the change in enthalpy of the reaction? Remember, the change in enthalpy of the reaction is going to be the difference between the products and the reactants. So that is going to be this piece right here. A, on the other hand, remember, is my activation energy. That's the energy that's required for this reaction to take place. So C is going to represent my enthalpy of my reaction overall. And this is going to be an endothermic reaction because my products have a higher potential energy than my reactants. That is the final slide for this video. Go ahead and rewatch as needed, take good notes, and come to class with questions.